So this is the second part of the series, What Derivatives Tell Us About the Shape of a Graph. In this short video, we'll discuss on which interval the function is concave up or concave down. So this is a concave up curve looks like. And if you sketch some tangent lines to this curve from left to right, you notice the patterns of the slopes of these tangent lines. Slopes are increasing. And the first derivative functions represents for the slope of tangent lines, which means the first derivative f prime of x increasing. And if the first derivative increases, meaning the second derivative is positive. So if you're looking at a concave up curve, you know that f first derivative increases and the second derivative is positive. And here is a concave down curve. And again, if you sketch some of the tangent lines along this curve from left to right, the slope of these tangent lines are decreases, meaning the first derivative decreases and the second derivative is negative. So if you look at a concave down curve of a function f of x, the first derivative decreases and the second derivative is negative. If we look at the graph of the functions, you see that the function is concave up on this interval and concave down on this interval. And the point where the function changes the concavity from up to down or from down to up is called inflection point. At inflection point, the second derivative equals to 0. So the question is, can we use the first and the second derivative of functions to identify on which interval the function is concave up or concave down? Okay. The answer is yes. Let's start with the domain of the functions, in this case from negative infinity to positive infinity, and you include the inflection point, in this case where we only have one inflection point. So this inflection point creates two intervals, negative infinity to inflection point, and from inflection point to positive infinity. And then we pick two test points on each of the interval, and we use the second derivative to evaluate this test point. The second derivative of a is positive, which means the function is concave up on this interval. And the second derivative at b is negative, which means the function is concave down on this interval. So we can conclude that f of x is concave up on negative infinity to the inflection point, and functions f of x is concave down on the interval from inflection point to positive infinity, right? So now we know how to identify the concavity of a function using the inflection points and using the second derivative, using the test point, and so on and so forth. The next question is, can you use these pieces of information to identify whether a critical point is a local maximum or a local minimum? In other words, how concavity of the functions can tell you about the local max and local min. So if you have a critical point that is located on a concave up interval, you see that that critical point is clearly a minimum, a local minimum, right? Which means if you plug the critical points into the second derivative, you get is positive, which means that critical point is a local minimum. And if you have a critical point that is located on a concave down interval, then the second derivative of that critical point should be negative. So then that critical point is a local maximum. Using the concavity of a function to identify local max and local min is when you use a second derivative test. Keep in mind that so far you have two tests which you can use in order to identify local max and local min, right? The first derivative test uses increasing and decreasing, and the second derivative test is using concave up and concave down intervals.